Welcome back for another deep dive. Today, we're going to be looking at Disentangled Representation Learning, DRL.
Okay.
Now, as experts in machine learning, data science, and math, I'm sure you're already pretty familiar with this idea of representations that capture the true underlying structure of data.
Right.
And DRL is really right at the heart of that quest. We'll be dissecting a research paper that gives a really fantastic overview of this field.
Yeah.
And our goal today is to equip you with a clear understanding of not just the definitions and the methods, but also the potential of DRL, particularly as it relates to your work.
That's right. This deep dive is really aimed at giving that comprehensive picture of the DRL landscape and, yeah, tailored to an audience with that strong technical background.
Okay, so let's unpack that fundamental definition of DRL. So the paper really emphasizes that disentangled representations should separate the distinct, independent, and informative factors that cause variations in the data.
Yeah, so imagine you have this data set of images of 3D shapes, right?
Mhm.
So a successful DRL model would be able to decompose those images into separate factors like shape, size, color, and even the viewing angle.
Interesting.
It's basically giving machines the ability to understand those generative factors behind the data, much like we do. The paper actually visualizes this nicely in Figure 1 using the Shape 3D dataset.
Okay, that makes sense. And I also noticed that the paper mentions a definition rooted in group theory.
Right, definition 2 formally defines disentanglement using concepts from group theory.
Okay.
And this framework, this mathematical framework, actually provides a more rigorous lens to view and analyze DRL. Figure 2 in the paper actually offers a visual representation of this group theory definition.
Okay, makes sense.
Yeah.
So the paper then goes on to create a taxonomy of DRL approaches, and it feels like there's a whole bunch of different methods out there.
It's true, there is. And the paper does a really good job of categorizing these approaches from 4 perspectives. The base model, the structure of the learned representation, the type of supervision that's used, and the assumptions about the independence of the factors. Figure 4 in the paper gives a really helpful visual roadmap of this whole categorization.
Yeah, definitely. So why don't we start with the base model types? The paper kicks things off with VAE-based methods.
Okay.
I'm curious, how are VAE's variational autoencoders being used for DRL?
So VAEs are these really powerful generative models that learn to represent data in a lower dimensional latent space.
Yeah.
So in the context of DRL, they're used to model that probability distribution of the data, and importantly, to impose those independence constraints on the learned representations.
Right.
So think of it as VAEs are trying to learn that compact blueprint of the data, and DRL kind of pushes them to make that blueprint as modular as possible.
That's a great way to put it. But the paper also highlights a challenge with using VAEs for DRL.
Right. The challenge really lies in balancing that disentanglement quality with reconstruction accuracy.
Oh.
So VAEs need to also be able to reconstruct the original data from their latent representation. So it's a bit of a balancing act, pushing for disentanglement while also making sure you don't lose too much information.
Yeah. So how do researchers handle that trade-off?
So one common approach is this beta VA method, which introduces a parameter to control that emphasis on disentanglement. This parameter basically acts as a dial, turning it up, increases that pressure for disentanglement, but it might come at the cost of that reconstruction fidelity. It's a trade-off that researchers are always trying to fine-tune.
Right, and the paper actually explores that in detail and presents that modified objective function.
Exactly, equation 4.
Okay. The paper also mentions some other VAE-based methods like DOK-VAE, factor VAE, and beta TC-VAE. Seems like they're all variations on this theme, but each with their own unique kind of twist.
Exactly. Each one introduces different regularizers or modifications to the objective function, all aimed at improving the disentanglement capabilities of VAEs. Table 1 in the paper actually gives a really comprehensive summary of these methods and their approaches.
Okay, definitely worth a closer look for those who are interested. Now, the paper then goes on to discuss VAE-based methods with group theory.
Right.
So we talked about that group theory definition of DRL earlier, and it seems like some researchers are directly embedding those group theoretic concepts into the VAE framework.
Exactly. And this provides a much stronger foundation for disentanglement. One example is the work of Quassard et al., which leverages group theory to actually learn disentangled representations in these dynamic environments. Yeah, their methodology and the specific equation they use, equation 16, are detailed in the paper.
Interesting. It seems like researchers are finding new and innovative ways to apply VAEs for disentanglement all the time.
Yeah.
But it's not the only game in town, is it?
No, it's not. The paper also discusses GANs.
Right, GANs, generative adversarial networks. So GANs are known for their ability to generate really realistic data. So how are researchers adapting them for DRL?
Yeah, a prime example is Infogan.
Okay, Infogan. Yeah, I've heard of that one.
Yeah.
So can you remind us how that works in the context of DRL?
Sure. So Infogan actually builds on that traditional Jan architecture by adding this variational regularization term to the objective function.
Oh.
And this encourages the Jan to learn representations where specific latent variables are really tightly coupled with specific aspects of that generated data.
So it's almost like creating this control panel within the Jan's latent space where each knob directly corresponds to a specific factor of variation.
You got it. It guides the Jan to not only generate realistic data, but to do so in a way that reveals those disentangled factors behind that data. Figure Notes in the paper provides a visualization of that Infogan architecture.
Oh, that's cool. And the paper also mentions other Jan-based approaches like IBGAN and PSC-VIN. It's really fascinating to see all these different methods emerging.
Absolutely. Researchers are constantly exploring new architectures and loss functions to push the boundaries of what's possible with DRL.
Right, and speaking of pushing boundaries, the paper introduces another exciting development, diffusion-based DRL methods.
Right.
So diffusion models, they've been making quite a splash with their impressive image generation capabilities. So how are they being used for DRL?
So diffusion models work by gradually corrupting data with noise and then learning to reverse that process to generate new data.
Okay.
A key example in the context of DRL is disdiff.
Disdiff, and what's the key idea behind that?
So disdiff actually disentangles representations within those gradient fields of the diffusion model itself.
Interesting.
It learns to separate out those generative factors while also simultaneously preserving that information needed to reconstruct that original data. It's a very elegant way to address that trade-off between disentanglement and reconstruction that we were talking about earlier.
Okay.
And the paper provides a visual representation of their network structure in Figure 7.
It sounds as disdiff is really pushing the envelope in both diffusion modeling and DRL.
It is. It's a testament to the creativity and innovation happening in this space.
Yeah, and we've only just begun to explore the landscape of DRL approaches. The paper goes on to talk about how these approaches differ based on the structure of the learned representation.
Right.
Which is something that we'll pick up in part 2.
Yeah, definitely looking forward to it.
All right, we'll see you then.
See you then. Welcome back.
All right, so let's dig deeper into the structural aspects of these DRL representations. What are some of the key distinctions that the paper highlights?
Yeah, so the paper distinguishes between dimension-wise and vector-wise DRL approaches.
Okay.
In dimension-wise methods, each individual dimension of that latent space is dedicated to representing a specific factor of variation.
Okay, so to stick with our 3D shape analogy,
Yeah.
you might have one dimension controlling the shape, another for size, another for color, and so on.
Exactly. Each dimension acts as that independent control for a specific feature. On the other hand, vector-wise methods use multidimensional vectors to represent factors, enabling more complex relationships between the factors in the data.
So instead of just simple sliders, now we're dealing with these interconnected controls that can interact in much more intricate ways.
Right.
So how do researchers decide which approach is more appropriate for a given task?
So the choice often depends on the complexity of the data and the nature of those generative factors.
Okay.
So dimension-wise methods might be suitable for simpler data sets with those clearly defined independent factors,
Right.
while vector-wise methods are better equipped to handle real-world data where factors are often entangled.
Yeah, that makes sense.
Yeah.
The paper offers a visual comparison of these approaches in Figure 8 and Table 2.
Yeah.
So it seems like vector-wise methods are kind of the heavy lifters of DRL. They're the ones that are capable of grappling with all the complexities of real-world data. Are there any specific examples mentioned in the paper?
Yeah, for dimension-wise methods, a lot of the VAE and Jan-based approaches we talked about earlier fall into this category. Okay.
They're often applied to those simpler data sets, like images of basic shapes or faces with controlled variations. For vector-wise methods, the paper highlights applications in more complex domains, like facial recognition and video analysis.
Oh, okay.
For example, drGAN uses separate vectors to disentangle a person's identity from their pose in an image,
Interesting.
allowing pose-invariant face recognition.
Okay.
Another example is MAP-IVR, which separates motion and appearance features in videos to improve activity-based video retrieval.
Wow, it's fascinating to see how these different structures are really tailored to these specific tasks.
Yeah.
The paper then introduces another layer of complexity, the distinction between flat and hierarchical DRL.
Right?
I'm curious to unpack that a little bit.
Okay, so we've been discussing these factors as if they exist on a single level,
Yeah.
but in reality, many generative factors have inherent hierarchical relationships.
Okay.
So think about a data set of faces.
Okay.
You might have a high-level factor like gender,
Which then influences those more specific factors like hairstyle or the presence of facial hair.
so it's like a tree structure with some factors acting as parent nodes to others.
Exactly. Hierarchical DRL aims to capture these relationships,
Right.
recognizing that some factors are kind of influencing others. And the paper visualizes this concept in Figure 9.
Got it. Can you give us an example of how hierarchical DRL is actually implemented?
Yeah, a good example is the VAE-based model proposed by Lai et al.
Okay.
They actually use a hierarchical generative probability model to learn those representations at multiple levels of abstraction. Their model architecture is illustrated in Figure 10. What's interesting is that their model actually learns progressively, starting with those high-level factors and then gradually refining its understanding down to those more specific factors.
It's almost like the model is building up its understanding of the data in layers.
Yeah.
Gradually moving from that big picture down to the finer details.
Exactly. And just like with dimension-wise versus vector-wise, the choice between flat and hierarchical really depends on the structure of the data and those generative factors involved.
So it's another important design decision in the DRL process.
Right.
So we've covered those base models and the structure of the representations. What's the next piece of this DRL puzzle?
So the paper then dives into the different types of supervision that are used in DRL,
Right.
which is crucial for guiding the model's learning process.
Yeah, we've been talking about factors and representations, but how does the model actually learn to disentangle them? That's where supervision comes in, right?
Exactly. And the paper actually categorizes DRL approaches into three main groups based on that type of supervision.
Huh?
Unsupervised, supervised, and weakly supervised.
Oh.
Unsupervised methods are the most challenging because they aim to learn disentangled representations without any explicit labels.
It's like asking the model to solve a puzzle without giving it any of the pieces.
Right. Unsupervised DRL relies heavily on imposing inductive biases on the model through various regularizers and constraints. However, there's an ongoing debate about whether purely unsupervised DRL is even achievable.
Really? Why is that?
Well, the paper highlights a fundamental identifiability problem with unsupervised DRL.
Okay.
Without any external guidance, the model might actually learn representations that appear disentangled, but don't truly reflect those underlying causal factors.
So the model could be fooling us into thinking that it understands the data when it's actually just learned spurious correlations.
Exactly. And that's where supervised DRL offers a more reliable approach.
Okay.
In this setting, the model has access to labeled data that explicitly identifies those factors of variation.
So in our facial image dataset, we might have labels indicating gender, hairstyle, and other relevant attributes.
Exactly. Supervised DRL provides that ground truth information to guide the learning.
So it's like giving the model a cheat sheet to help it along.
Yeah, essentially it is. And it leads to more reliable disentanglement.
Okay.
However, obtaining labeled data can be expensive and time-consuming.
Right, so it's not always feasible.
Exactly. And that's where weekly supervised DRL comes in. It kind of offers that middle ground.
Okay, so it falls somewhere between those two.
Exactly. A weekly supervised methods might use a small amount of labeled data or leverage other forms of weak supervision like data grouping or partial annotations.
So it's about providing the model with some level of guidance without requiring those exhaustive labeled data sets.
Exactly.
It seems like there's this whole spectrum of supervision strategies that are being explored in DRL.
Absolutely. The choice of supervision type really depends on the task, the available data, and the desired level of disentanglement.
Right, so we've now covered the base models, the representation structures, and the types of supervision used in DRL. What's next?
The final aspect that the paper explores is the independence assumption,
Okay.
which delves into the relationships between those generative factors themselves.
Right, because we've been talking about these factors as if they're always independent of each other. But I imagine that's rarely the case in real-world data.
You're right. Most traditional DRL methods do operate under that assumption of independence between factors. However, there's a growing recognition that factors can have complex and often causal relationships.
Right, so acknowledging that the color of a car might be influenced by its make and model, or that the presence of facial hair might be related to gender.
Precisely. And this is where causal DRL comes into play.
Okay.
This emerging area aims to explicitly model those causal dependencies, moving beyond that simplistic independence assumption.
That seems like a pretty significant step forward. What are some of the key approaches being explored in causal DRL?
The paper highlights causal VE as a prime example.
Okay, causal VE.
This method incorporates structural causal models, or SCMs, into its framework to represent those causal relationships between factors. Figure 12 in the paper provides a really clear illustration of this concept.
So causal VE is not only trying to identify the factors, but also to understand how they influence each other.
Exactly. And while causal DRL is still relatively new, it holds immense potential for developing AI systems that can reason about cause and effect. Right.
Leading to more robust and reliable models.
This has been a really deep dive into the inner workings of DRL. We've explored this wide range of methods from VAEs and JANs to diffusion models. We've delved into the structural aspects of those representations, the role of supervision, and even the emerging field of causal DRL.
It's been a great discussion.
But before we get too carried away with all the possibilities, I think it's important to address this question of evaluation. How do we actually measure the effectiveness of a DRL model? How do we know if it's truly learned disentangled representations?
You're absolutely right. Evaluating the quality of that disentanglement is paramount.
Yeah.
And luckily, the paper dedicates a whole section to exploring those various metrics that are used to assess DRL models.
Okay, perfect.
Which is actually where we'll pick up next.
Okay, so let's dive into this world of DRL evaluation. So we've built these models, but how do we actually know if they're doing a good job? How do we measure how effective they are at disentangling those representations? Right. Evaluating disentanglement is really crucial, and as you said, the paper dedicates a whole section to this, looking at those various metrics used to assess DRL models. And one fundamental distinction is whether the metrics are supervised or unsupervised.
Okay, that makes sense. So supervised metrics rely on having that ground truth information about those factors of variation.
Exactly. It's like having that answer key and seeing how well the model's representations line up with it.
Right. So what are some of the common supervised metrics that are used in DRL?
One widely used metric is the Disentanglement Completeness Informativeness Score, or DCI for short.
Okay, DCI.
This metric actually evaluates three key aspects: how well each latent dimension corresponds to a single factor, that's the disentanglement part, how well all factors are captured by the latent representation, that's completeness, and how much information each dimension provides about its corresponding factor, that's informativeness.
So DCI sounds like a pretty comprehensive way to assess the quality of disentanglement when those ground truth labels are available. Are there any other supervised metrics worth mentioning?
Yeah. The paper also describes metrics like mutual information gap, or MIG and ZDIF.
Okay.
MIG measures the difference in mutual information between the most informative latent dimension for a given factor and the second most informative dimension. A large gap indicates better disentanglement.
Okay.
ZDIF involves training a classifier to predict the value of a factor based on the latent representation, and higher accuracy suggests better disentanglement.
So these supervised metrics provide really valuable insights when we have those ground truth labels. But what about situations where that labeled data is scarce or even unavailable? How do we measure disentanglement in those cases?
That's where unsupervised metrics come into play.
Okay.
They rely on those intrinsic properties of the learned representations without needing access to ground truth labels.
So trying to assess disentanglement based on the internal structure of those representations themselves.
Exactly.
Are there any examples of these unsupervised metrics?
One prominent example is the beta VAE score, which is specifically designed for evaluating VAEs. It measures the correlation between changes in those individual latent dimensions and changes in the generated data. Low correlation suggests that each dimension is independently controlling a specific factor.
Okay.
The paper also mentions the factor VAE score, which builds upon that beta VAE score by adding a penalty term that encourages the model to avoid learning spurious correlations between those latent dimensions.
So it's making sure that that disentanglement is real and not just an artifact of the model overfitting to the data.
Exactly.
So these unsupervised metrics are really valuable for evaluating DRL models when labeled data is limited. It's great to see such a variety of evaluation techniques available. So we've covered the definitions, the methods, taxonomies, even how to evaluate those models. But I'm curious, what's the real-world impact of all of this? Where is DRL actually being applied?
DRL is having a pretty significant impact across a wide range of fields. One of the most prominent is computer vision, where it's being used to improve tasks like image generation, domain adaptation, image translation, and even video prediction. So for example, in image translation, DRL can be used to disentangle factors like lighting and content, allowing you to manipulate these factors independently to generate realistic images under different conditions.
So DRL is not just improving those existing techniques, It's enabling new capabilities altogether.
Right. And the paper highlights applications in natural language processing, where it's being used for text style transfer, topic modeling, and text generation.
Wow.
It's also being used in multimodal learning, where it helps bridge the gap between different data modalities like images and text, enabling things like image captioning and text-to-image generation. DRL is also being explored in recommender systems, graph representation learning, few-shot learning, and even addressing out-of-distribution problems where models need to generalize to unseen data.
It's really remarkable to see the breadth of these applications for DRL. It's a testament to the power of disentangling those representations. So before we wrap up, I'd love to get your perspective on the future of DRL. What are some of the key challenges and opportunities that lie ahead?
Well, the paper outlines several exciting future directions. One key challenge is developing a deeper theoretical understanding of disentanglement.
Hmm.
We need more rigorous mathematical frameworks to define and evaluate it, and to understand its relationship to other important concepts like generalization and robustness.
Okay.
Another challenge is scalability. Many current DRL methods struggle to handle those massive, complex data sets that are becoming increasingly common.
Right.
Developing new techniques that can efficiently disentangle representations from these large-scale data sets is crucial. And finally, a major opportunity, and maybe even a necessity, lies in integrating DRL with powerful foundation models.
Yeah, those foundation models.
Models like large language models and text-to-image generators have shown remarkable capabilities, but they often lack transparency and controllability.
All right.
DRL has the potential to enhance these models, making them more interpretable, controllable, and ultimately more aligned with human values.
So DRL isn't just about making AI more capable, it's also about making it more responsible and trustworthy.
Exactly. DRL has that potential to help us build AI systems that are not only intelligent, but also aligned with human goals and values.
Well, this has been a fascinating deep dive into the world of DRL. We've explored a lot of ground from those fundamental definitions and methods to the exciting applications and future directions. And I hope our listeners have gained valuable insights into this rapidly growing field. As you continue to explore the world of machine learning and AI, keep in mind the power of disentanglement and its potential to really shape the future of intelligent systems. Until next time, keep diving deep.